Now that we've actually programmed the PIC, let's take a look at everything that we did. Because some of you are probably sitting there going, what on earth did I just do? I know Floduino on Jetpack Academy had already burned through the lessons and said he was proud of himself for getting the PIC programmed and up and running. And you should be. This first run through is very challenging, mostly because of MPLAB. But after this first time through, I think you'll find it actually really simple. Just a matter of programming your code, burning the PIC, and testing the program. MPLAB actually really makes things overwhelming in a hurry, but as you'll see, it is actually a very powerful tool for building projects and testing them without even programming a chip. So, take a look at your code. Let's dissect it. The very first two lines are for the compiler and are actually not our instructions. The compiler needs to know which microcontroller we're using. You saw the list. There's like hundreds of them, and each one is different. Different addresses for the ports and registers, different numbers of ports, registers, encoders, etc. So these two lines simply tell the computer which chip we're using and to load the information file for that chip, which came with MPLAB. The information file is called an include file, and you can see the extension here, .inc, for include. You'll notice as well these semicolons and random notes after them. Notice also that the text is in green when you're in MPLAB. Semicolons mark whatever comes after them as a comment. Comments are your comments. They can be whatever you want, and they are notes to self, and the compiler ignores everything that comes after the semicolon. So when writing your code, it's good practice to throw in random comments explaining to yourself what each line does. Believe me, when you get into like 100 lines of code or more, you'll be thankful you left yourself notes. The next two big lines might wrap around and appear as 4 or even 6 lines on your screen because they're so long. These are configuration settings, and we call these settings fuses. You'll remember for the clock, we had several options. We could use an external clock like we did, or you could use a resistor-capacitor pair on the outside of the chip to change the clock speed, or we could use a crystal to lock in the clock at an exact speed, or we could use the built-in clock. Now that is a critical option, and it is set by one of these commands, specifically this one. FOSC for frequency of oscillator. Now I'll show you how to work with these fuses later on, but we call them fuses because that's originally what they were. The configuration settings were EEPROM. You burned off the fuse when you programmed the chip, and these specific EEPROM settings set up the configuration of the chip. Now there's a whole mess of configuration settings in these two lines. We'll just ignore them for now though, okay? This next line actually doesn't need to be there, but I actually put that in there to save on confusion. All that will happen is when you go to compile your code, MPLAB will spit out a whole mess of like information warnings. They're really just information, but they're worded in such a way as to like set off alarm bells in your head. They imply that your assembly code is all messed up and it's not working, when in fact there's nothing wrong. So by including this line, the compiler doesn't spit out these warnings, and this just saves on confusion. So everything up until this point was configuration and setup for the compiler and the chip itself. Now we get into our actual assembler code. Here's all of the mnemonics. Let's take a look at what they did exactly. The very first line, I already explained what the mnemonics were. But let's explain, but not exactly what they did or why. The first one, bank select, is needed because of a unique way the PIC micros are built. Now, if you open up your PIC datasheet and go to page 30, you'll see the first of several pages of register banks. Now, these are lists of registers, and you see that they are split up into banks of 128 registers at a time. Now, it's complicated to explain, but basically they designed the architecture of the PIC micros this way so they could easily expand the chip. If they wanted to add more registers or RAM, they simply added another bank. By doing this, the same instructions could be used on all of the PIC chips, no matter what their configuration. The downside is, to change any specific register, you have to specifically state which bank you want to work on. Because you'll call that register by, say, register 23 in bank 15, not register 23 in bank 1. They are two different registers. So in our first line of code, you'll see we're trying to set up port C's tri-state register, TRIZ-C. Now let's look for it. There it is, in bank 1. So to set the TRIZ-C register, I have to first set the bank pointer to bank 1 in our code. I do that with the bank select command. And I could give it the specific address of the bank, 01 in hexadecimal, but I did it in a slightly different way. Because of that very first line of code, where I told the compiler to include the information file on the PIC16F1455, one of the things that information file contains is where registers are located within the chip, including what bank they are located in. So instead of telling the chip in plain English to change the bank to bank 1, what I told it was change the bank to whatever bank register TRIZ-C is located in. The compiler then goes to the information file, looks up the TRIZ-C register, finds out what bank it's in, and compiles that into the machine code. Now, why did I do it this way? The reason is because let's say I now want to use a different PIC controller. The assembly language and my program is exactly the same. However, on that particular PIC, the TRIZ-C register is actually in bank, say, 3. So if I had put in bank cell hexadecimal 01 in my assembly code, I would have to now go through my entire program and find every instance where I selected bank 1 and change it to bank 3. By referencing the specific register I want to address instead of an actual bank address, the compiler goes and looks up the bank address for me. So now, when I switch chips, the only line I should have to change is the first two. I'll simply tell it what chip I'm using, and boom, it loads the include file. So my first instruction selects bank 1 so I can access the TRIZ-C register, which is in the next line of code. CLRF means clear the file, and in this case I want to clear the TRIZ-C register. This clears all of the bits in the TRIZ-C register, or sets them all to zeros. The TRIZ-C register controls port C. Port C is connected to several pins outside of the chip, and each of those pins can either be an input or an output. You can see the pins in the pinout listed as RC0 through RC5. So bit 0 controls bit 0 on port C. If the control bit in the tri-state register is 0, then the corresponding bit in port C is activated as a digital output. So now, when I write either a 0 or a 1 to that bit in port C, the output pin goes either low or high. If the bit on the tri-state register is set to 1, then the pin on port C is activated as a digital input. So I can now access that pin and read whatever high or low is on that pin. But because it's very different electronics as to whether I use that pin as an output or an input, I have to set the state of the pins. And I do this with the control register TRIZ-C. So I just went ahead and cleared the TRISC register. I set all the bits to 0, which means all the pins are now set as outputs. The next line points us to another bank, the bank containing register LATC, or the latch on port C. The latch C register is where we write our output for port C. So we're now going to write to the latch port, so we simply select its bank, getting ready to write to it. The next line is what we call a label. Now labels are a sort of marker. Labels, you can give it whatever name you want as long as the name doesn't match a register or a command. For example, I could call my label Fred or home base or any randomly made up combination of letters and numbers. But I can't label it bank cell, for example. Bank cell is an instruction, a command. And so that word is reserved. It would confuse the compiler if you tried to make a label called bank cell. The compiler would be going, "Hey, qu'est-ce que c'est? You want me to select a bank for you?" So this particular label I made as loopy1, but be careful, it's case sensitive. If I put in a second label, loopy1, but with a capital L, that is a different label than loopy1 with a lowercase l. So if you go down here a few lines, you'll see the command go to loopy1. Basically, it'll run these lines of code, get to this command, and it sends it back to my label called loopy1. So you can see where I'm going with this. I just want to run this series of commands in a continuously running loop forever and ever. Amen. Now, labels are the only thing that will be all the way to the left in our code, in column 1. Even the command go to is even indented. Okay, so once we've established our label, our marker, we then see this command, which I had already previously explained, move LW, or move a literal number, into the W register, the working register. So if you remember, the arithmetic register, the one that does all the math and has that huge bank of complicated digital circuits attached to it, in the PIC micros, it's called the working register. So with this command, we're telling it to load the working register with hexadecimal FF. The H tells it the number in quotes is in hexadecimal. Now, I could have put in a decimal number of 255, which is the same number, and I just simply changed the H to a D. Or I could put in a binary, 1111, in place of the H. Whatever I put in there, whatever I put in the quotes, is the literal number, and it will put that number into the working register, so you can do whatever work you want to do with that number. In this case, the work we want to do is the next command. Move WF, or move the working register to a file. So this command now takes whatever number is in the working register and puts it into another register of your choice. In this case, the latch C register. So if you can picture it, our latch C register had all zeros in it. We loaded up the working register with all ones. And now we put all of those ones into the latch C register. The latch C register is the outputs of port C. So we just set all of the output pins on our port C to high. Our LED was connected to bit 3 of port C. All of the bits of port C just got set high, so the LED now turns on as it sees a high. So if I had loaded the working register with binary 00001000 and then sent that to the latch, that also would have turned on our LED because it's turning on bit 3. Remember, the least significant bit is bit 0, which corresponds to our C0 on port C. I just stuffed an FF in there because, well, I could. I didn't have anything connected to any of the other port C pins, so it didn't matter. Let's turn them all on and off. So now our port C is set high and the LED is turned on. Now we need to turn the LED off by setting bit 3 on port C to 0. Now I can do that with the CLRF, which is clear the file or register, and then followed by what register we want to clear, and that would be latch C. We have now cleared all the bits on port C, set them to 0, so the LED now extinguishes. The next line in our code sends us back to loopy 1. We now load the working register with FF, send it to LATC, turning on the LED, then clearing the latch, turning off the LED, then going back and doing it again. Because all of these commands are driven by the clock, we are relying on the clock to turn the LED on and off. But you remember some commands take more clock cycles than others? If you're fast, you can count the clock pulses while your pick is running the program. Once it gets running and gets into that loop, it takes 4 clock cycles to clear the latch and turn off the LED, but it takes 16 clock cycles to go back to the beginning of the loop, load the working register, and transfer the working register to the latch, turning on the LED. So this is why we set up the pick to operate from a ridiculously slow clock, so you can actually see and count the clock pulses required to fulfill the commands we've issued. So let's move on to the next lesson where we'll control 4 different LEDs from port C.